Hello and welcome to a short little sample video where we're going to go through some examples of how to find these probabilities, z-scores, and then just normal x values using Excel. So let's start with just z-scores, which are the distances that we have when we're dealing with a standard normal curve, right? So it's been standardized so that the mean is 0, right? And the standard deviation is 1, and that's what a z-score is. It tells us how far above or below we are from that middle of 0. Well, we can find these areas under the curve very easily using technology. You don't have to rely on silly tables and things like that that you might see in textbooks. And in Excel, it's super easy with the equals norm dot dist for the normal distribution function. And then the first thing you're going to give it is the z-score. Then you're going to give it the mean. Then you're going to give it the standard deviation. And then you're going to choose true or false, or you could type in true or false. Now, specifically, we can think of this z-score as really an x value, which we'll see later. But basically, you're just going to give it the value you're working for, and then the mean, the standard deviation, and then you do true or false. Now, some things to realize. The norm distribution function gives you area below it. So it's perfectly set up to do this one. So if we just do equals, right, norm dot distribution of 0.44, comma, remember the mean is 0, the standard deviation is 1, comma, true, because true just says give us the cumulative area below it, and then false says give us the area just at that value, which is a different thing completely. We're doing the cumulative distribution function, not the probability distribution function. But anyway, if we run that in Excel, it will give us the area below 0.44, which is exactly what we need. However, if we want to do the second one, right, where we need the area above, well, remember that if we do norm dot distribution of negative 1.04, it's going to give us area below. And so we're going to have to subtract that from 1, because remember the area under the entire curve is just equal to 1. So this really is quite easy. You can do it all at once. I mean, you could just run the norm function, get the answer for below, and then you subtract it from 1, manually, or do it in Excel with another function. But you could do it all at once by just saying equals 1 minus the norm dot distribution of negative 1.04, comma 0, comma 1, comma true. And it does the math for you. It already takes 1 and subtracts the normal distribution from it. Very simple, very easy. And then to find area in between, well, we just have to remember that if we do the norm of this, it's going to give us all of this area, right? Everything below the 1.28, all the way out there. So it's going to give us this white area that we don't want. So then if we come back and we also do the norm distribution of 8.4, it's going to give us this stuff in the white area that we don't want. So hopefully you all can see that very simply, all we have to do is take the upper one and subtract the lower one from it. And again, you could do that all in once, or you could do them individually in your own little cells and then, subtract them afterwards. Try not to do things by hand, like try not to have the displays in Excel and then go to your calculator, and because now you're rounding and rounding and rounding. Always try to use Excel and say, hey, take this cell and subtract this cell from it and give me my new answer if you want to do that. Or get more comfortable with doing these things all at once. And it's really simple, right? I mean, we would just do equals, and I'm just going to do ND, right, for norm dot distribution, just because we're going to run out of space. So we're going to do the ND of the 1.28, blah, 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 and then minus the norm dot distribution of the negative 0.84, And if you do that, it just does all the work for you right there in that one cell. So it's a really simple, easy process to do these types of things in Excel. All right, so let's take a look how we might set up an Excel spreadsheet to be able to do these types of questions for us, kind of create our own personalized calculator. So we're going to need to know the mean, right, standard deviation. We're going to need to know the sample size for future questions. We won't need it for this one because right now we're just sampling one thing, right, and we're just looking for a z-score. Later on, we're going to need to know what the new square root, what the new standard deviation is, and this comes from the central limit theorem. So just put that in for now, and we'll deal with it later. And then we're going to need to know what the x value is, the thing that we're trying to find. Now you might want to call it x, and maybe in parentheses z to remind yourself that the z-score is really just an x value when we're on the standard normal curve. That's really all it is, right? It's the same kind of data value we would have. An x is our data value, but it's been normalized to the standard normal curve, so it's now called a z-score, but it's the same thing. And then we can make some calculators that will do the math for us, right? So in the cell next to this, I'm going to find the probability of being less than that x value or greater than that x value. And then if I need to do an in-between, well, then I need to know what my second x value is, or my second z-score, so I just called it x2. You can call it whatever. And then down here, I'm reminding myself that this is where I find the area in between those two things, right? So between x2 and x, which also reminds me that x2 needs to be the bigger of those two values. Okay. And then you might also want to just put percent and x down here because we're going to use these for some future examples as well. So you can get it all set up right now. Okay, well, the first few things are all you're just typing in, right? So there's nothing in these cells as far as formulas are concerned. We're just going to give it a mean and so on and so forth. So for this first example, our mean is 0. Our standard deviation is 1. You can see things are already starting to change. This one here, of course, we need to define this as the standard deviation divided by the square root of n. So we're going to make it, right, b2 divided by the square root of b3 because that's my standard deviation square divided by my the square root of my sample size cells, right? So that's going to give us that computation later. This is just a fill in the blank, right? This is just a fill in the blank. So for this first example, we wanted to be, less than 44, less than this, and then over here we want to be in between. So let's go ahead and jump straight to the in between and see how we can get kind of all of it at once. So our upper value was 1.28, and our lower value is negative 84. So 1.28 is the big one, right? And then negative 0.84 is the low one. Now we can already see that this would have given us the area below, remember, below this one. So this would be the area below negative 0.84. This would be the area above it. And then this is the area in between the two. Well, how did we get each of those? Well, again, it's just using the simple norm.distribution function. And all you have to do is instead of typing in these values, you define them by their cells. So remember, the first value has to be the x or the z-score that you're testing with. So that's why it's got the B5 right there, right? Then the next one has to be the mean. So there's my B1, then comma. The next thing has to be my standard deviation. And what I've done for my computations is I've set them all up to use the central limit theorem. And you'll notice that when our sample size is 1, this cell and this cell are exactly the same. So I could actually just tell this to pull this cell instead of I'm having it do the computations all over again. So let's change this. Let's make this simpler on ourselves. So for this formula, we can just say, let's pick this cell. We're always going to do the central limit theorem version. And again, we'll talk about that later, what it means. But for now, it's just the same thing as if we would have picked the standard deviation up here, right? Standard deviation of 1. So these two cells are the same because if you divide by the square root of 1, you're dividing by 1 and you get the same thing. And then it's always going to be true, right? So there's that amount. So just so you know that I'm not lion. If this is a 5, look what happens. This is also a 5, right? So they're always going to be the same. Okay, but in any case, that's how we get below. If we want to get above, we can just do 1 minus this cell, but we also could have done 1 minus norm dot distribution, blah, 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 and it would give us that. But since we already know that it's always just going to be the complement of this, we can always use 1 minus whatever that cell is and kind of save us the hassle of having to do the norm function twice. Okay, here's the thing that we just type in, right? Nothing changes there. And then here's that one where we do the in-between, right? So we have to do the top one minus the bottom one. Well, since we've already calculated the bottom one, we can just use that cell. We don't have to type in, a norm dot distribution of the top value and then subtract the norm distribution of the lower value. So that's what I did here. You guys, again, you could change this up to make it simpler. You could always just have it go back to your standard deviation cell if you wanted to do that. But it'll set us up nicely for when we have to do these probability questions where instead of just picking one thing, we're going to pick a set of things. What's the probability if you pick 5 things that their average is blank? Well, then we have to use the central limit theorem, and then we have to use this adjusted version. Okay, so that's how simple that is. What happens if we need to go in the other direction? That they give us the area under the curve, right? That's what this means, is this green little area is a little bit more than 30% of the total area, right? And this green area over here is a little bit more than 20% of the total area. And they want us to find the corresponding z-score that gets us back to that area. Well, that's just as easy. It just uses a different Excel function. And, they're even good about titling them similarly. So this is going to be equals norm dot inv for inverse, because we're kind of doing the inverse norm function. Instead of, hey, you give me a z-score, I give you an area. Now you give me an area, and I go backwards and give you a z-score, right? That's an inverse function. And we still need to know the same information, and we do it in the same order, right? So the first thing we need to know is the z or the x score. Then we need the mean, and then we need the standard deviation. And we don't need to worry about the whole true or false thing because we're always dealing with area. So we're basically always in the true camp of the cumulative function. Okay, so it's that simple. If we go back to, obviously this one would be 1 minus using the 0.2, just like before, right? These are always area below. So the inverse is the same way, area below. If you wanted to find this z directly, you could just do 1 minus this, and that'll give you the area below, right? So it makes it really easy whichever way you want to do it. But in any case, okay, so here is where we put in the percentage. This is the area they give us, and then here is the function, right? Norm.inverse. You can see that the B12 is picking up the x value, or in this case a z-score when we do it, and then the next one is B1, that's the mean. The next one is, I did that whole B2 minus the square root stuff, but I could also just make this B4 if I wanted to. And then that's going to give me the z-score that comes back from that area right under the curve. Okay, so the first example, we wanted to find 0.3050. All right, so this is going to be 0.3050. And there's my z-score. And you notice how it's negative. Well, look at the picture. See how it's below 0? It should be negative. Okay. Now let's see what happens if we put the 2061 in here. So 0.2061. It's also negative. And you go, but wait a minute. This isn't negative. It's above here. Remember, this function always gives you the area below, right? So starting from 0 up to. So what's happened when we put in the 0.2061 is it's giving us the mirror image of this area over here of being 0.2061. And it found this z-score. Well, if this z-score is negative, what did we get? Negative, let's just do negative 0.82. Okay? If this z-score is negative 1.82. What do you think this one is? Because of the symmetry of the normal curve, we know that it has to be the exact same number, the exact same distance from the mean, only now in the positive direction. So this is literally 0.82. So, you don't have to worry about finding 1 minus this. But, if you feel more comfortable doing that, then why not go in here and change this to equals 1 minus that. And now that gives us the area below, and look what happens. We just get the exact same answer, only now it's positive. Now you might say, hey, the last one was 82003, and now we're getting 82028. It's just because we got one extra decimal because it didn't have to put the little minus sign in front of it. So it's literally the exact same number. It's just the other one was rounded to one fewer places of accuracy. And that's it. I mean, that's how easy it is to do these. It doesn't change once we change from a z-score to a regular question. Like, okay, now instead of z-scores, we're going to deal with an actual set of data, like IQ scores. And IQ scores of adults are normally distributed with a mean of 100 and a standard deviation of 15. And now they want us to do the exact same thing. Find areas under the curve, but instead of giving us a z-score, they give us IQ scores. Now, if you wanted to, you could, of course, convert all of these to z-scores, right? You could use the simple z-score formula. Your z-score equals your x value minus the mean all over the standard deviation. So in the case of this first one, right, a z of 118 would equal 118 minus the mean, which is 100, all over 15. We get 18 over 15. And if we stick that in our calculator, we get 1.2. So we could go to our Excel calculator spreadsheet, leave the mean at 0, leave the standard deviation at 1 because we now have a z-score, right? And our z-score was 1.2. And it tells us that the area below is 0.88493, okay? So we know this is 0.88493. But what if we didn't want to hassle with converting them to a z-score? Let's just use the raw data of 118 and then the 100 and the 15, right? So now it's 100 is our mean, our standard deviation is 15, and now we want to do 118, and look what we get, 0.88493, 0.88493, the exact same thing. So it just depends on if you want to keep creating z-scores, you can, but why would you when all you got to do is change the mean and the standard deviation? And we can see how it's going to be the same for all of these, right? If we want to do area above, we're just going to do 1 minus it. If we want to do area in between, we're going to use the same little between process. And then if we want to go backwards, right, if they give us a question and says, hey, now find the IQ score that corresponds to this stuff, well, we do the same thing with the inverse function, only now we have to change the mean and the standard deviation, right? Or again, we would have to do z-score stuff, which is a big pain in the butt algebraically, so you don't want to do that. Instead, just change it, right? We've already set this function up to pull the mean from here, right? And the standard deviation from here. Well, technically the standard deviation of this divided by the square root of that, but we're still doing a sample size of 1. But in any case, to do this one, all we have to do now is use 0.9099, 0.9099, and then we can see that a z-score, or sorry, in this case an IQ score of 120, if we round to the nearest whole number, 120, would give us an area of roughly 91% below it, which means an IQ score of 120 is kind of what you would consider the 91st percentile, right? Because 91% of the data is below it, i.e. you have an IQ score that is higher than 91% of all other IQ scores, all other adults, basically. It's telling you you're in the top 9%. You're very, very smart, that kind of thing. And you are very, very smart, right? Because you understand this. This is simple. This is easy. We can do z-scores or we can do actual data values all we have to do when we do actual data values is change our mean and standard deviation to the data, sample statistics that we have, rather than using the simple mean of 0 and a standard deviation of 1 when we're dealing with z-scores. And that's how we can do all this stuff with Excel.